So hopefully you have watched the videos. The one from White Goodman from Dodgeball perfectly explains game theory. You know what the other players are going to do. They know what you're going to do. And you know that they know what you're going to do. And they know that you know what they're going to do. And you have to behave accordingly. So it's not at all confusing, especially after White Goodman cleared it up for us. So now that we know how game theory works, let's get into it. We have what's called a payoff matrix. Now, there's also what's known as a game tree. It's when one player goes first and then the other player responds, and you can have different outcomes mapped out that way. When you have sequential moving, some principles classes cover that. It's one that I think lends itself better to coverage at the intermediate level and beyond. So I don't go into that too much here. Instead, we just keep it simple with the payoff matrix where we assume that everybody moves at the same time. There is something called a first mover advantage in some games. Other games, you actually don't want to be the first mover. But again, it's intermediate and advanced and is actually really fascinating if you have a, kind of a geek's brain like mine. But I would encourage you to continue taking economics after this class just to study that and for no other reason. But whatever, we're going to assume that everybody moves at the same time. There's no first mover, so we're only going to have payoff matrices. And this is the formal definition of a payoff matrix, and this is basically what it looks like. This is a very generic form. Don't let this make you think that game theory is more complicated than it is, though it does get pretty complicated. What this payoff matrix does, usually in this box you'll have the name of the player. Player 1, player 2. Row player goes here. That's the player who can make decisions by choosing this row or that row. Column player, we generally say column player, but it can be player 1, player 2. We'll also see firm 1 and firm 2. Or firm 1 here and firm 2 here, where firm 2 is the column player. So you choose this column strategy or that column strategy. We have up, down, left, and right are kind of the generic names. Oh, this is a 2x2 game. You can have matrices that are larger than this. There's also an n by n player game where you essentially have an infinite number, but again, that's beyond the scope of this course. So for just the simple 2x2 player game where the column player moves at the same time as the row player, once they make their decisions based on the other player's decision, these are the payoffs. And these payoffs can all be equal. Some payoffs can be equal to others, but we label them as the payoffs that correspond with a different strategy set. Again, this is very generic. It's never going to be this generic again in my class. But if the row player chooses up and the column player chooses left, then the payoffs are A for the row player and B for the column player. Convention is that the first number in the payoff matrix always goes to the row player, and the second number goes to the column player. So if the row player picks down and the column player picks right, the row player gets G. Whatever that payoff is, that's what the row player gets, the player who picked down, and the column player picks H. So let's look at an actual payoff matrix. A game theory is used to describe a lot of things, as a brief aside here. And this is assuming that you watched that clip from the Batman, the Dark Knight, the Batman movie that has the Joker in it. And you have prisoners and regular people on a boat, and they can blow up the people on the other boat and save themselves because they know that the other people have bombs on their boat, and you can use game theory to describe this. Some people have said it's the prisoner's dilemma. It's an example of a prisoner's dilemma. It actually kind of isn't. We'll get into what all of that is. But this kind of goes into the example of the fact that game theory isn't just for studying oligopolies, in case you're wondering why we're branching off into game theory here. Game theory can describe it's used to describe a lot of different things. Back when people were afraid that the Soviet Union and the United States would blow each other up in what was known as the Cold War, everyone thought there's a real possibility that the other side is going to launch a full-on nuclear attack and they're going to kill us all and we're going to launch and kill them and mutually assured destruction. Economists tended to be the ones who advocated mutually assured destruction because game theory predicted, usually in the form of what's known as a hawk-dove game, that if we assume that both sides are rational or are run by people who are rational, which is never a good assumption, we're talking about politicians. However, rationality can mean different things. Here it means, do you have something to gain from your actions? Well, politicians have been studied by economists who ask the question of, does the politician personally have anything to gain from a given set of decisions? And if the personal gain is some sort of monetary gain from being corrupt, then corruption is what we predict. It's actually why some economists assume that politicians should be presumed corrupt just in general. That's the rational thing to do. So the rational thing to do as far as the Cold War is concerned is to have the outcome be exactly what it turned out to be. Don't launch your nukes. Because if you launch, you have nothing to gain and everything to lose. If you launch and the other side doesn't, you might gain something, but because you can't assume that that's going to happen because they're looking at the same payoff matrix, then you got to assume that they're not going to launch unless you do, so everybody's better off if nobody launches. That's the game theory way of going. There's game theory and all sorts of other things. These are just some examples of how game theory is a very versatile and useful tool to analyze the incentives and then predict the outcomes. There's also a great paper that my game theory instructor at CSU, Stefan Kroll, you ever go there, take his classes. He's a delightful man. He's a great, great teacher. Learned a lot from him. Excellent teacher of game theory too. He gave us a journal article. It's a great read, even if you don't typically read economics journal articles, that had some of the 10 jewels of game theory and some of the 10 basically areas where game theory did a great job of predicting outcomes, and areas where game theory said that these are the outcomes that should happen, but because human behavior is complex, something else happened. It's a very interesting way of looking at how theories can be very useful, but they can also be somewhat misleading, but can still be important, and very interesting ways of analyzing human behavior. So, applying this to the Joker's social experiment, there are a lot of ways you can set this up, but the important thing is that if everyone blows everybody else up, we basically saw them emerge here where nobody blew anybody up, and this might be the set of incentives that they faced. If everybody blows everybody up, everybody's dead, you don't get a payoff. And we can get into non-economic discussions about what happens after death and how you die, and maybe you do get a payoff. But as far as rewards here in life, you're dead, you don't get anything else, so you get a 0. Row player here was nice, column player blew them up, so they got blown up, so they got 0. Getting to live is worth something, but you got to live because you blew people up and gave them a 0, so you got a guilty conscience. So that's not as good as being nice and getting to live. That's the best of both worlds. So perhaps everybody saw that they're guaranteed a 0 if they blow up the other boat. I'm sorry, they're going to get a 0 if they're blown up either way, but the biggest reward is to not blow anybody up. Now, this is close to game theory, because it might actually be rational to try to get yourself a 1. You hit the button first. I know we talked about simultaneous movers. This is what we study in this class, but this is where the others decided not to. For whatever reason, you blew them up first. You kind of guarantee yourself a 1. But you get a 2 by being nice. But this isn't technically a prisoner's dilemma. To be a prisoner's dilemma, this payoff has to be higher than this one, but this has to be the highest payoff of them all. Here, the absolute highest payoff is right here. And thinking strategically, the others are looking at this payoff matrix, and what you know is that whether you're normal people looking at prisoners or prisoners looking at normal people. Sorry, prisoners are normal too, but you know what I mean. Whoever you're looking at, you know that they're seeing the same. Obviously, they didn't think like this in that clip. You probably wouldn't do it in real life. But if you have any awareness of the fact that the best payoff for everyone is for no one to blow anybody up, you might just say, I'm not hitting the trigger button either, because not only will I get to live, I'll be able to get to live without that guilty conscience here that gives me just a 1. So this would predict that everyone would just not kill anybody. And if the Joker had seen this payoff matrix, he might not have gone to all that trouble to try and see a whole bunch of people blow everybody up so he can prove that everybody's as crazy as he is, or whatever his motivation was. So this is one way to apply prisoner's dilemma to other things, but it's technically, or not prisoner's dilemma, game theory to other things. This is an example of prisoner's dilemma. And because, as you know, I make 80s and 90s references, I figured I'd go back and make, what is this, a 1920s reference or something? Stay mum, don't say anything, or, hey, they finked on ya. I guess maybe for some people I need to translate. Mum means that you don't say anything. Fink means that you're a snitch. So in the prisoner's dilemma, the classical setup for the prisoner's dilemma is two people get caught committing a crime. They're arrested and they're put in separate interrogation rooms. And then they're offered deals. And from the standpoint of the police basically have enough evidence to convict both criminals of a lesser charge. And they get a light sentence. They need the confession of at least one of the criminals to be able to get the more serious charge for anybody. But of course, if you cooperate, if you talk, you get maybe a lighter sentence. So these are years of jail time served. So if nobody talks, if you both keep your mouths shut, then the police don't have enough to convict you. But they get you on a lower crime. You're still going to do prison time, half a year, 6 months, then you're out. If the role player doesn't talk, but the column player is a rotten snitch, what you can say when you confess to the crime is, that other guy held a gun to my head and made me do it, or whatever, to basically get the police to say, okay, you cooperated with us, and we really don't have any evidence to convict you of any crime other than the lighter charges, but because you cooperated, we're not even going to get you for that. You get to go free, while your partner in crime gets the entire sentence all for themselves. And we're assuming there's no coming back later and saying, okay, he snitched on me, I'm going to snitch on him, or anything like that. Again, we don't like to complicate things in economics. Don't get too realistic. This scenario is where both rat on each other. So now the police are saying, we have enough to convict you both, so we're convicting you of that serious crime, but instead of 5 years, you only get 2 because you both cooperated with us. So what this is saying is that this is what's called the social optimum. Everyone jointly, together, is better off here than they are here. So you would think that looking at this would cause both to say, this is what I'm going to do. I'm going to keep my mouth shut. Problem is, the penalty, if the other person doesn't do it, is pretty stiff, while the reward of not having to spend any time in prison is pretty nice. The payoff is much better here than it is here, even if this payoff is better than this one. So what Prisoner's Dilemma illustrates is that the mutually beneficial outcome that's best for everybody, that's not always what we expect to see. The incentives could be for an outcome like this that isn't so nice for everybody. You would rather have 0.5, 0.5 than 2 and 2. That's what you'd rather have. But that's not what's always going to happen if the incentives are set up like in a standard prisoner's dilemma. So again, what on earth does any of this have to do with economics? Well, it turns out that oligopolists who can't formally collude and form a cartel because they'll go to jail, and there have been CEOs of companies who've gone to jail because they were caught talking to the heads of other companies trying to convince them to keep their prices high. That's not a good way to get this kind of arrangement that you want. So oligopolists are in something like this. They are basically in a prisoner's dilemma. You use the prisoner's dilemma to understand how oligopolists make the decisions they make and whether they're going to make a lot of money or not much at all. And that we will get into in the next